Hello everyone. This part is linear transformation. It's from section 1.8 and 1.9. We're going to learn what is linear transformation and what we mean by standard matrix for a given linear transformation. Of course, we want to identify the standard matrix for each linear transformation. And there will be basic transformation mentioned. And linear transformation, we want to know the concept can be converted to a matrix vector multiplications. All right, the definition. What is linear transformation? First of all, a transformation is a broad concept of a mapping from a domain D to range R. But linear transformation has to satisfy two conditions. T mapping to U plus V can be separated as the sum of T of U and T of V. Here U and V could be any two points in domain. And we want to have another condition. T mapping on C times U is the same as C times T of U. Here C is scalar, a number, and U could be a vector in the domain. All right, let's get back to one example we mentioned in the first lecture. So there was a picture on the left-hand side and converted to or transformed to another picture on the right-hand side. And that transformation is given by, for any x1, x2 in the domain, so any two-dimensional vector in the domain, after transform, it goes to different coordination, which is the first coordinate is horizontal coordinate is transformed to half of x1 plus x2. The second one stays the same. And that kind of transformation gives us this kind of picture from a square to another parallelogram. Now we want to prove this is a linear transform. So to do that, we want to check two conditions. So the first condition is we want to check T of U plus V equals TU plus TV. The second condition I'm going to check is T times CU is going to be C times TU. So let's start with the first one. Because T is defined as for any vector, it goes to second new vector with 1/2 x1 plus x2 and x2. So we are going to use the definition of T. From left-hand side, we start with left-hand side and come up to the right-hand side. That's the whole proof. So if I have U plus V, because they are two-dimensional vector, I can write it as U1, U2 plus V1, V2 and the whole thing. So T maps on this vector, sum of vectors, and the sum of vector is actually U1 plus V1, U2 plus V2 by vector rule. And then by the definition, the mapping goes to half of the first coordinate and second coordinate. Second coordinate is the same. Now we're going to separate that to match the right hand side of the equality. So this means I'm going to separate u and v terms. So combining the like terms of u1 and u2, it becomes half u1 plus u2 plus half v1 plus v2, and second one is u2 plus v2. And by vector addition, we can separate these two. One half u1 plus u2 and u2. The second one is half v1 plus v2 and v2. By checking the definition, first term is the same as tu. Second term is the same as tv. This is the first proof of the addition. And the proof of scalar multiplication is following. So T is mapping to C u1, u2. And that by vector multiplication gives cu1, cu2. And we know that after transformation, the first coordinate is half of the first coordinate plus second coordinate, and second coordinate doesn't change. And then we want to separate that. Oh no, this time we cannot separate anything. But what we can do is we can take out C. So from vector multiplication, this is the same as taking out C and 1 half u1 plus u2. And this is u2. So that gives me, by definition, tu. Alright, this is the proof why the given transformation is linear. Alright, so we know, if we know a transformation is a linear thing, then we can implement this linear transformation by computer. But in your programming, you must tell a computer what to do. And what to tell in computing, this is something we won't understand here. So suppose T is a linear transformation, mapping from n-dimensional space to m-dimensional space. Now, there's a rule saying that when there exists a unique matrix A such that T of x equals A times x. So linear transformation, in terms of linear algebra, it's a multiplication of a matrix and vector. And this matrix has a special name, so-called standard matrix. And this standard matrix is something you want to input in your programming. Now, the second point is, given a linear transformation, to tell the computer what you want to do, you need to tell the computer the standard matrix. Then how do you identify this standard matrix? So the rule is following. The standard matrix corresponding to T is the same as TE1, TE2, TEn. Here, what is E1, E2, En? Those are all vectors in Rn space. So it's called standard basis. So standard basis in Rn space is a set of vectors consisting of E1 is a vector of 1, 0, everything else will be 0. And E2 is 0 and second component is 1 and other things are 0. And all the way down, En is 0, 0, 0, and the last one is n. So if we translate this rule, this is an important rule. So if we translate this rule, it can be said, given a linear transformation, to identify its standard matrix A, you want to map linear transformation to standard basis, and you get a collection of new vectors, TE1, TE2, TEn, and put them together in a box. That gives you a matrix, which is standard matrix. Now, we are going to practice this rule using the previous example. So we have a linear transformation from two-dimensional space to two-dimensional space. And I want to know what the standard matrix is. And we can see that here standard basis in R2 is that two vectors, 1, 0, which is E1, and E2 is 0, 1, just two. Then what you want to do is, what is TE1? TE1 is half of the first coordinate and plus second coordinate, which is 0 here, and second coordinate does not change. And TE2, similarly, we have half of 0 plus 1, which is 1 and 1. So the standard matrix A here is supposed to be 1, half, 0, and 1, 1, gives the 2 by 2 matrix. In this slide, we're going to give another example, so-called rotation transformation, which is pretty useful, and it is very common in Photoshop or any image processing. So imagine there's a transformation from R2 to R2, be the linear transformation that rotates each vector about the origin through the angle phi counterclockwise. We can think of phi as 45 degrees. Then the standard matrix is called rotation matrix, which is just given by this standard matrix, which is 2 by 2 matrix. And the visualization is from image processing is following. If you have a certain polygon here, and after you take rotation phi, then you're going to end up with another new polygon. All right. The question is, given this kind of definition, rotate angle phi counterclockwise, how do you determine this matrix? Without telling you this 2 by 2 matrix in advance. So we can check the standard basis. So standard basis for R2 is going to be E1 equals 1, 0, and E2 equals 0, 1. Now we want to get the standard matrix, we want to transform each E1, E2 to a new coordinate. So after transform, so we can think of E1 as here, 1, 0, and after phi, rotation. So we have to work on a unit circle with radius 1. So after rotate this phi like this, then the new point will end up with here. And this, from trigonometric function knowledge, this is cosine phi and sine phi. So that gives me the coordinate cosine phi and sine phi. And TE2, then that means we're going to map 0, 1, which is supposed to be here. Starting from here, rotate along a circle phi, then you're going to end up with this red dot. And this is phi, and this is phi. So what we have is the new coordinate will be cosine phi plus pi over 2, which is 90 degrees, sine phi plus pi over 2. And then we can check the trigonometric formula, which can be written as negative sine phi, and this is cosine phi. So put them together. This is TE1 and TE2. Put them together. This gives you 2 by 2 matrix. All right. This is the whole lecture, and thanks for listening.